Hello everyone and welcome to another video. So today we are on to week 9 of our AE511 class. So this is getting near the end of the quarter. We're coming into the home stretch, week 9 out of 10. So we're almost there. So let's take a look at what we're going to be talking about during week 9. So if you remember last week, week 8, we looked at basically talking about PID controllers, and we looked at how to design them, how to synthesize them, what were some of the problems that you might run into with PID control. And now I'd like to spend week 9 looking at another strategy, and this is the strategy of what's known as full state feedback control. So we're going to need to talk first, before we get into full state feedback, we're going to see that one of the prerequisites before you can bring this tool to bear is that you need the system to be controllable. So we're going to talk first about what does that even mean? How do you tell if a system is quote-unquote controllable or not? So this discussion here, it gets a little bit more mathy, but I think it's interesting. We're going to talk about what is something called the controllability matrix as well as the PBH test. So these are two ways that you can tell if somebody gives you a linear system, you'll be able to know, is it controllable or not? If it is controllable, then you might be able to use full state feedback control. So I want to talk about, well, first of all, what is full state feedback control? How can we implement this? And this first one is, how do we do this academically? What's the ideas? How can this theoretically work? And then, just like we did with the PID controller, I want to then next look at, okay, now that we understand what a full state feedback controller is and how it's supposed to work, if you try to do this in real life, in a practical implementation, what are some problems you might run into? So again, we'll look at the nice, fine academic theory here, and then maybe ask ourselves, where might this break down, or where can it go pear-shaped if we try to do this in the real world? So that's the game plan right now. Is week 9 is all about full state feedback control. So that being said, maybe let's take a look at the homework to see how is that related. So the homework is actually pretty straightforward this week. It's a little bit shorter, which I'm sure is going to be welcome to everybody. The first problem is I'm just going to give you a linear system. Somebody's going to drop this linear system in your lap. So it's got an A matrix, it's got a B matrix. In this case, you can kind of see it's only got one input signal, right? One control, because this B matrix only has one column. So all we're going to look at first is, tell me if the system is controllable or not. And you can do this using both the controllability matrix and the PBH test. So again, if you watch this video, it's going to be very clear how to do this. It's going to be pretty darn straightforward. Now, that's going to allow you to then say, okay, if the system's controllable, you can make a full state feedback controller. If it's not, you're a little bit, well, you might be out of luck. Let me just leave it at that for now. But I want you to look at this now is, okay, based on your results from part A, can we even do part B? Can you even make a full state feedback controller that's going to move the poles to some arbitrary location? And if you're able to do this, how about let's just pick some location. Say you want the closed loop poles of the system to be at -4, -5, -6, -7. How can you find me a full state feedback controller gain K that is going to do that? Well, if you're able to do that, part C is basically just, well, simulate the closed loop system to some non-zero initial condition. Look at the response. Say you move this thing to this state initially, just let it rip under a full state feedback controller that you designed in part B, and tell me what's going on. Part D is kind of interesting, and I don't know if I want to talk about it too much right now. I really think if you watch this video over here, especially near the end, I talk a little bit about some of the nuances in the different subspaces, the linear subspaces that the PBH tests bring to bear. So what I'd like to do here is basically just test this for all the eigenvectors of the A matrix. So show that this is full rank, this right here. This is basically testing that this matrix inside here is full rank for every eigenvalue. But overall, the A matrix and the eigenvalue are uncontrollable. So if the B matrix was this eigenvector, I want you to show that it's uncontrollable in that case. So again, this is one of these problems where I think if you just read it and then watch the last part of this video, part D, is going to make sense. But it's basically just writing a couple of lines in MATLAB, doing a little bit of linear algebra checks to look at the rank of a matrix, and I think you should be off to the races. And then same thing with part E. I think once you watch the video, this is going to make sense. And again, all I'm asking for is just saying, show that this A matrix with this fictitious B matrix, which happens to be the linear combination of all the eigenvectors, just show that that is controllable. Okay, so that's problem one. It's all about controllability, and yeah, that's about it. Problem two is, let's now look at a little bit simpler, but also a little bit more complicated system. So in this case, you've got a 3x3 system, and you've got two inputs. You can kind of see here, the B matrix is 2 columns, and you have 3 outputs. 1, 2, 3, because the C matrix is 3 rows. And more importantly, if you look at the C matrix long enough, you see it's the identity matrix. So actually, we have all the outputs are actually just the states, right? So that's basically what I'm trying to state right here. Okay, so again, part A, I think you can show that this A matrix is open loop unstable. So if you don't do anything, this system is not headed for success, right? One of these signals is going to exponentially grow to positive or negative infinity and probably take a few other states with it. What I like to then ask is, okay, in part B, let's say you only had one control, basically only this first column. Is the system controllable? So like this is like, maybe think about it, it's like a car. You have a steering wheel and a gas pedal. Is it controllable only using the steering wheel? How about only using the gas pedal? How about using both the steering wheel and the gas pedal together? Now, in these 3 different cases, is the system controllable? Once we answer that, I'd like to then ask ourselves again, let's consider that this system starts at some weird non-zero initial condition. And now I'd like to design a whole bunch of different closed loop control systems using full state feedback. And we're going to do that according to this mapping. So all we're saying here is when k equals 1, you can kind of see that we're not asking for a very aggressive system, right? I'm asking to put the closed loop poles at -1, -1.5, -2. So it's a little bit in the left half plane, but it's not really far in the left half plane. So you can kind of think of k equals 1 as the sort of less aggressive controller situation. But I want you to just change this value of lowercase k from 1, 2, 3, 4, all the way up to 10. So you can see when lowercase k is 10, that basically is shifting all of these desired closed loop poles farther and farther into the left half plane. So you should be getting more and more aggressive controllers. And what I like to do is just run 10 different simulations, each with a different set of these desired poles locations, which are then going to yield a different full state feedback controller. And I just like people to comment on the behavior. As you do this, what are the changes in the controller? What are the changes in the control signal? What are the changes in the state trajectory, etc., etc.? And just think about some of these questions, right? And maybe as a little bit of a spoiler alert, what I'll let you know right here is I think you're going to see that full state feedback controllers are powerful, but it's a little bit difficult to kind of get it to do exactly what you want. It's going to kind of evolve as it wants to. It's going to be hard to tie pole locations to actual physical signals. So long story short, what you should probably be answering down here is that it's not super duper easy to persuade the controller to favor one signal over the other, okay? Little spoiler alert, the reason I'd like people to start thinking about this right now is because that's going to set the stage for what we're going to be talking about in week 10, when we're going to investigate a technique called linear quadratic regulator, which is a form of full state feedback control, which is going to allow us to kind of ameliorate some of these challenges that we're investigating here in homework 9. So, with that being said, that's the game plan here. We're getting near the end of the quarter, so we're going to look at full state feedback control, then roll right into LQR control next week, and that's going to pretty much be the class. So, this is probably a good spot to leave it. Let me know if anyone has questions. Otherwise, I'll look forward to talking with everyone over email or at our next office hours. Okay, thanks everyone. Bye.